you want to streamline your commissioning process, go paperless, and increase efficiency? Our software digitizes your custom forms and checklists, allows collaboration across project teams, and automates reporting. Plus, it's easy to use. With hands-on support, we will get you set up and operating confidently with Blue Rhythm in no time. You can even use our templates. Contact us for a demo or start your free trial today.
Good afternoon, everyone. My name is Sam Schwartz, and I'm a Member Engagement and Marketing Manager for the ABC Commissioning Group. Thank you for joining us for the first installment of ACG's Essential Commissioning Webinar Series. Every month for the rest of 2020, we'll be hosting a new presentation covering different facets of the commissioning process. These webinars are endorsed by CABA, the Continental Automated Buildings Association, and this particular webinar is sponsored by Blue Rhythm Commissioning Software. I'd like to go over a few housekeeping notes before we get started. We encourage you to submit questions at any time using the Q&A button on the bottom part of the player. A few will be selected to answer towards the end of the webinar, and the speakers will answer the rest via email afterward. The chat function is where you can make general comments and chat with attendees. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists. And then finally, in terms of continuing education credit, you will receive an email after the webinar with instructions on how to get your proof of attendance using ACG's CX Energy app. Today's webinar is Chase Center Arena and Mixed Use Development, High Performance Design at Mission Bay, with Eric Sheffer and Clark Denson. Eric is a principal and sustainability consultant at SSR. He works on projects across the US to help create energy efficient and sustainable buildings. Eric worked as part of SSR's multidisciplined consulting team for the Chase Center. Clark is a senior building performance engineer at SSR. He is an expert at assisting project teams that design cost-effective and high-performing buildings across all market sectors. Clark was also a key member of SSR's project team for the Chase Center. Thank you again, everyone, for joining us. And with that, I'll hand it off to our presenters to kick us off today.
Thank you. So thank you, guys, for kicking us off today. I'm Clark Denson, here with Eric Sheffer, as Sam said, and we're excited to talk about our project. Eric, why don't you, I'm going to move on to the next slide and let you get us started.
Perfect. Yep. Thanks, Clark. I can see the first slide here. We appreciate everyone out there joining us today, again, for our virtual session on high performance design at Mission Bay, the Chase Center and Mixed Use Development. We hope that you, family, and colleagues are all staying well out there during this time. We're looking forward to spending roughly the next hour with you to talk about general sustainability approaches, goals, and a deep look at the energy efficiency design at the Chase Center, home of the Golden State Warriors. So as Sam mentioned, your presenters today are Clark Denson, Senior Building Performance Engineer at SSR. He was the primary energy consultant and energy modeler for the Chase Center campus. And in the second part of the presentation, he will be doing a deep dive into the energy systems approach. As Sam mentioned, I'm Eric Sheffer, principal with SSR. I was on our sustainability consulting team. And in the first section of our presentation, I'll be talking about the overall sustainability goals and approach to LEED and green building certification. Our learning objectives today are to, number one, describe the overall sustainability and energy performance goals of the project. Two, explain how climate and energy analysis were used to identify applicable and cost-effective design solutions. Number three, we'll be describing the approach to high-performance systems design. And number four, we will show how energy modeling was used to demonstrate compliance with codes, LEED, and the Savings by Design incentive program. As you can see here from this nice photo rendering, the Chase Center is situated in the Mission Bay neighborhood of San Francisco. It's located on a rehabilitated brownfield site. in the neighborhood. As you can tell, looking north and to the west, you have a great view of downtown San Francisco, and then north and to the east, there's also a beautiful view of the San Francisco-Oakland Bay Bridge. The major program and design elements on the Chase Center campus are, again, obviously the Chase Center Arena, home of the Golden State Warriors. It also has an associated retail complex with it. There are two large office towers. The North and South Tower are also known as Mission Bay, 3 and 4 office buildings. They comprise almost 700,000 square feet of commercial office space, and Uber will be occupying those buildings next year. And finally, the Gatehouse, which is that sort of the entryway or gateway to the campus. And the Gatehouse houses both amenities as well as a small broadcasting center. Okay, to just kind of start out here with a brief overview of the sustainability goals for the project. First and foremost were energy efficiency and carbon reduction, followed by water efficiency and reuse. I'll go into great detail about the water efficiency approach. As a team, we wanted to do our best to decrease single passenger transportation for carbon reduction and other reasons we'll look at. Site sustainability, indoor environmental quality, material sustainability, and construction waste management was another large focus of the project. To give you all an overview of how we approach LEED certification for the campus, it's nuanced when you have a site with several different buildings that will be applying for LEED certification. And for this project, our project team, we chose to pursue a LEED campus project application. And in order to do that, we registered what's called a master site with the GBCI on LEED Online. And through that master site, we registered individual LEED projects for the Chase Center Arena and the North Office Tower and the South Office Tower. We are really excited to announce that just within the last 2 weeks, the Chase Center was LEED Gold certified. The entire project team and the city and region are really proud of that accomplishment. The North and South Office Towers, the core and shell of those buildings are also LEED Gold certified. The interiors of those buildings are currently pursuing LEED Gold certification, and the office towers are also pursuing WELL certification. And then what the campus application allowed us to do for this project was to create shared sustainability criteria and shared documentation that can be where the same information can be applied globally for these campus credits across all of the projects, with the focus for the campus application being the sustainable sites credits and criteria, water efficient landscaping, the approach to operational recycling, which I will talk about, the approach to construction waste management, which I'll talk in detail about, as well as environmental tobacco smoke control. So to share with you the overall LEED approach and scorecard for the Chase Center, again, just recently LEED Gold certified. You can see at the bottom right, we did achieve 71 points for the LEED certification, which with a threshold of 60 points to achieve gold. The largest credit category that had numerous sustainability initiatives and the most LEED points was sustainable sites. Again, initiatives in that credit category that netted us points for LEED were locating the site on a brownfield, having it in a densely occupied community with services that were within walking distance to the site, alternative transportation being pursued at many different levels, which I'll talk in more detail about, stormwater design and heat and reduction of the heat island effect. After sustainable sites, we received 20 points in energy and atmosphere. Clark will talk in detail about the approach to optimize energy performance, energy modeling, and how we achieve the 13 points for energy efficiency. An enhanced commissioning process was implemented for the Chase Center, as well as green power. Indoor environmental quality was also a focus of the project. Sustainability criteria in that credit category included outdoor air delivery monitoring, a focus on low emitting materials, controllability of comfort, and thermal comfort. Water efficiency, again, I will go into detail about the water efficiency approach for the campus, and we achieved 8 of 10 points in the water efficiency category. And then the other primary category was materials and resources, and we had a focus on that category in sustainable materials and construction waste management. So this project had a really interesting and comprehensive approach to water efficiency. It resulted in an overall 84% total potable water use reduction potential for the Chase Center and the campus, with the potential to save upwards of 2.8 million gallons annually. About a third of that savings, or roughly 1 million gallons, is based on high efficiency water fixtures, from faucets to water closets to showers and others within the facilities. About half of the potable water being saved on the site can be attributed to a detailed recycled gray water system, where we on the campus are collecting condensate from the IDEC units from the office towers, collection of gray water from office tower lavatories and showers, as well as collection of and reuse of stormwater from all the impervious surfaces on the roof areas. The recycled water system can treat about 40,000 gallons at a time. It's actually shown, a lot of the equipment for that system is shown here in this photo, and actually behind that concrete wall is the storage area for the gray water recycling system. And that water is reused in water closets and urinals in all of the buildings, as well as site irrigation on the campus. And we wanted to just share, you know, as folks on the phone can imagine, if you've ever designed a gray water treatment and recycling system on a multi-building campus with getting the gray water from multiple sources, treating it, and then pumping it out to various sources for reuse, as you can imagine, it's relatively complicated. This was just a nice diagram that was put together by the plumbing team, where at the top left, you can see incoming gray water from showers, lavatories, and HVAC condensate. At the upper right, incoming gray water from impervious roof surfaces. Both of those sources come down to gray water storage and treatment. They are treated. Obviously, there's you know, provisions for overflow, and then they are pumped out to reuse on the site in the form of flushing urinals and water closets, as well as site irrigation. Another big focus for the project was sustainable construction and construction waste management, and diverting as many materials and waste from the landfill as we could for the project. The project team worked to create a detailed construction waste management plan that identified recyclable materials and estimated volumes, potential vendors and location for recycling diversion. And this resulted in 18,000 tons of waste diverted from the landfill for recycling, which constituted about 87% of all waste on the project. The waste that was diverted from the landfill primarily consisted of wood, metals, gypboard, and then the fines and the other materials shown here on the right as mixed inerts. Those were mostly either demolition materials or hardscape materials that were ground up and reused on the site, either as road base or in other areas of hardscaping. Moving into sustainable operations, it was really important to the warriors and the stakeholders on the campus to have a comprehensive transportation management plan. Our goal there was to promote a reduction in single passenger vehicle travel to and from the site to both reduce carbon emissions and reduce traffic implications to the surrounding neighborhoods. One primary method is a neat bike valet system that was designed within the Chase Center. And you can see here the photo to the right. That's some of the bike valet equipment, where if you ride your bike to an event at the Chase Center, similar to checking a coat, you can get a tag, check your bike. They will hang it here in a secure area. And when the event is over, you bring your tag and get your bike back. The city did provide additional BART public transportation stops. The site overall, compared to overall occupancy, has very limited on-site parking. However, within that parking, there is vehicle charging stations for electric vehicles, as well as designated carpool parking. Okay, and finally, to round out the sustainability overview here for the project, again, focusing on sustainable operations at the facility, ongoing waste management during operations and events at the campus is very important to the warriors and the stakeholders on campus. There's an aggressive rate of diverting 70 to 80% of waste to be diverted from the landfill and either composted or recycled in the form of food waste. Paper and cardboard, metal, plastics, and wood will all be targeted for diversion. And then finally, there will be corporate policies enacted for the site, including green housekeeping, as well as ongoing purchasing of green power and renewable energy credits. And with that overview, I will turn it over to Clark to do a deep dive into the energy efficiency approach and energy modeling at the campus. Clark, take it away.
All right, thanks, Eric. And so yeah, for the next few slides, we're going to be talking about talk about how we use energy modeling throughout the design process to inform the design of the Chase Center and the adjacent buildings on the Mission Bay campus. First and foremost, I want to stress that building energy modeling is truly the Swiss Army knife of the building design process. From asset ratings to retrofit design, it can be used in multiple ways depending on the demands of the project. And out of these many ways, energy modeling was used in this project in Mission Bay to aid in architectural design, HVAC and controls design, code compliance, lead, and financial incentives. So this started very early in the project, even as early as the concept phase, when the design was barely more than a sketch on the back of a napkin. We evaluated the local site and climate to determine what climate-specific and passive design measures might be the most appropriate for this project. And looking at the climate data for San Francisco, we first noticed that it's in ASHRAE Climate Zone 3C, classified as warm, marine, and it's a pretty temperate climate with not a lot of hot days. So this lends itself to a lot of days with free cooling economizers and perhaps natural ventilation if a building lent itself to that strategy. Taking a deeper look at the data, we investigated what other strategies might be used most often in this climate. We saw that two-stage evaporative cooling could be effective. We saw that high-performance low-E glazing, especially with clear glass on the south facade, might be effective at promoting passive solar heating. And because of the cooler temperatures in this climate, we found that architectural shading probably wouldn't be very effective, as we tended to need all the passive solar heating that we could use to offset mechanical heating. And finally, the cooler temperatures made high-efficiency heating systems more cost-effective. So out of these strategies mentioned, one that was used for many of the buildings throughout the campus was two-stage evaporative cooling, also referred to as indirect direct evaporative cooling, or IDEC for short. This essentially works, and so this building, this strategy was used for particularly the office buildings and the arena. And this strategy works by essentially using water rather than energy for cooling. And you can use either of these stages, the indirect or direct stages of evaporative cooling, independently for smaller cooling effect. But for this project, both were bundled together. So with direct evaporative cooling, air is blown across a water-saturated medium, usually cellulose. And when water evaporates directly into the airstream, it reduces the air's dry bulb temperature while increasing the relative humidity at a constant wet bulb temperature. And this is accomplished with very little energy other than the power for a small spray pump and some additional fan power to overcome the pressure drop of the wetted media. So indirect evaporative cooling is similar in that a secondary airstream is cooled directly by evaporation of water, but this air then goes through a heat exchanger, which then indirectly cools the primary airstream. Therefore, indirect evaporative cooling does not add moisture to the primary airstream, so both dry bulb and wet bulb temperatures are reduced. And so we don't really see this technology used a lot east of the Mississippi, where we tend to have higher outside air dew point temperatures. But in drier climates and in the marine type climates, as Asher calls them, this is a much more effective strategy due to their lower outdoor dew point temperatures. So the first project we're going to take a closer look at will be the two office buildings. Each is 11 stories tall and about 300 to 330,000 square feet each. And the energy goals for these buildings were to comply with the 2013 California Title 24 Energy Code, as well as achieve LEED Gold certification under the 2009 LEED Core and Shell rating system. So in terms of energy analysis, we began early during the schematic design phase to engage in a load reduction analysis. So this type of analysis is often useful and important because it identifies measures that, in the best of cases, are shown to reduce not just energy, but also first costs. And at the very least, they can make these load reduction strategies more cost effective if you take advantage of the reductions in HVAC first costs. So we investigated various load reduction strategies associated with building envelope, from increased insulation in the walls and roof, improved U values of the windows, and improved solar heat gain coefficients of the windows. As you'll see here, note that the U values shown for the windows are center of glass values, just provided for comparison's sake, though the model U values took into account the framing as well. So we looked at not just a reduction in energy, but also reductions in peak heating loads and peak cooling loads. And as you can start to see, there are some measures that are more impactful from others and may have a bigger bang for the buck. So next we engage in a financial analysis, first using the RS means to estimate each measure's effect to envelope costs. Now, as you can see, when you compare this with the annual energy cost savings, many of these measures resulted in a payback period of 6 to 12 years. And this probably was not very attractive to most owners, but fortunately, the contractor was able to provide cost estimates for the HVAC systems as well. So we added these to the overall equation, and we see that many of these measures reduced heating and cooling loads enough such that when you take that into account, and not just the increase in envelope costs, but also the decrease in HVAC costs, you start to see that the payback periods reduce dramatically, many of which getting below that magic 3-year payback period that many owners are looking for. So I think what we can safely say is that energy savings alone probably wouldn't have been enough to justify a high performance envelope for this project. So as the design progressed and we came up to our final design, the final design consisted of a high-performance curtain wall with low E glazing and also insulated spandrel in certain areas. And that insulated spandrel had very similar characteristics to the wall load reduction strategies that we analyzed earlier in design. From an HVAC standpoint, the majority of the building was served by multiple zone VAV IDEC units. that had supplemental water-cooled DX coils, gas preheat coils, air side economizers, and though the design originally had VAV boxes with electric reheat, they were eventually changed to hot water reheat. Supplemental to that in a few areas were water source heat pumps and a fluid cooler that served all that water-cooled equipment, as well as a high-efficiency condensing boiler for hot water. As a result, the LEED energy model demonstrated a 12% energy cost savings to the Title 24 2005 baseline, which LEED used as the baseline for this rating system, and earned us 5 Energy and Atmosphere Credit 1 points. And as Eric indicated, the buildings achieved gold certification. So moving on to the Gatehouse. Gatehouse was a small but interesting project at 9,000 square feet and located at the heart of the Mission Bay campus. Its primary purposes were to serve as a broadcast area for pre-game and post-game events, as well as a bar and lounge area for visitors and VIPs. And though this building was small enough that it didn't have to comply with the Cal Green building standards and the San Francisco Green building standards, like the Chase Center Arena and the office buildings had to, it still needed to comply with the Title 24 Energy Code. And that was enough of a challenge. And as you look at this rendering, this image from the energy model, you may get a hint at why that may have been the case. So we'll get back to that. As I mentioned before, the 2013 California Building Energy Efficiency Standards, also known as Title 24 Part 6, was the applicable energy code for this project for permitting purposes. And like many energy codes, such as the International Energy Conservation Code and ASHRAE Standard 90.1, Title 24 has several mandatory requirements that always must be met, regardless of which compliance path you take. Then you have to choose to follow the prescriptive, you can choose to follow the prescriptive approach, which consists of several more requirements and potential exceptions. Or if the team can't meet or chooses not to meet one of these prescriptive requirements, they have the choice to follow the performance approach. So this performance approach, it allows for a wider variety of design strategies and provides a greater flexibility than the prescriptive approach allows. And furthermore, it provides a way to find the most cost-effective way to comply with the energy code. To do that, you follow what Title 24 calls their approved calculation method, or the ACM. Essentially, this means that you choose from a list of approved energy modeling programs that follow the ACM and the ACM's rules. Now, California has developed their own code compliance software called CVEC-COM, which can be used as a standalone program, or you can use one or two other programs that have incorporated the ACM's rules and or uses CVEC-COM as a compliance engine under the hood. These programs are the IES Virtual Environment and Energy Pro. So to comply with the performance approach, you must use energy modeling software to show that the proposed annual time-dependent valuation, or TDV, is less than the baseline annual TDV. Because TDV, again, the time-dependent valuation, is the energy metric that Title 24 uses to judge code compliance. It's not the same as site energy, not the same as source energy, and not really energy cost, but I like to relate it most closely to energy cost with a time of use rate structure, because it not only considers the type of energy that you're using, such as electricity and natural gas, but also when it's used throughout the day and throughout the year. So energy saved during periods when California is likely to have a statewide system peak, saving energy during those times is worth more than saving energy during times when supply exceeds demand. And so, TDV, it depends on your fuel type, as I mentioned, the time of year and time of day, depends on your building type and your climate zone. And due to all this, consequently, as a general rule, I've kind of found that finding ways to reduce electrical demand is a key to success for complying with Title 24. So, getting back to the Gatehouse, as you may have thought, one of the primary challenges for the Gatehouse to comply was glazing selection. This building consisted of a lot of glazing, 5-foot vertical sections supported at the bottom and structurally glazed along the vertical seams. The basis of design glazing assembly consisted of 2 panes of glass laminated together, probably to aid in impact resistance. And you can see that there's no air gap and there's no low E coating because at the time, the budget just wouldn't allow for it. Now keep in mind that these were not flat panes of glass. They were specially manufactured curved windows. And with a budget of $500 per square foot, at the time, it was felt that double-paned insulated glazing units were considered cost prohibitive. So by contrast, the Title 24 baseline used a 40% window-wall ratio, as well as double-paned IGUs with an airspace and low-E coatings on surface number 2. Therefore, we knew that code compliance would be a challenge. And to mitigate this, we collaborated with the rest of the design team to come up with potential energy conservation measures that could be evaluated to help with code compliance. So we looked to incorporate LED lighting extensively throughout the building. The architect thought maybe we could evaluate shading the glazing by recessing them a few inches into the framing. We looked at evaluating water source heat pumps rather than 4-pipe fan coil units, and also looking at some alternate glazings that fit within the project budget. So when we ran our first iteration of the energy model about early to midway through the design, as you suspected, the basis of design at the time with the laminated glazing and fan coil units wasn't quite complying. So we evaluated those other measures such as recessed glazings, the alternate glazings with a low E coating on the room side of the laminated glazing, as well as water source heat pumps. And we found that with a combination of those, we could comply. And so going forward, the team used water source heat pumps and the laminated glazing with room side low E as the basis of design going forward. So fast forward much later in design, at this point, we're talking with manufacturers to get products ordered and shipped, to get the glazing products ordered and shipped. And we knew that the laminated glazing wasn't going to comply. However, our basis of the design, our new basis of design with the laminated with the room side low E, we're running into some problems. We discovered late in the game that the North American manufacturer of this glass couldn't provide our order due to scheduling conflicts. And so looking at kind of offshore manufacturers in Europe and maybe it was Asia, they couldn't manufacture the curved glass with the room side low E. So we're kind of stuck between a rock and a hard place. And eventually the team kind of went back to the drawing board and decided to instead use an insulating laminated glazing with a low E coating on surface number 2. This had a much lower U value and it complied with code. And though it originally was deemed to be too expensive for the project, it was ultimately chosen for the project. So that was plugged into our final energy model, and the energy model showed that the project complied, and just barely, primarily with helping from savings from lighting and the heating and cooling systems. In reality, the building is probably operating much more efficiently than the model suggests. And the reason for this is that this particular version of CBEC-COM that was used for the project couldn't model variable speed fans in water source heat pumps. And while we could have probably used some workarounds and post-processing to show slightly higher compliance margin, as we had done earlier during earlier iterations of the model, our final model was able to demonstrate compliance without such workarounds. And so this brings us to the crown jewel of the Mission Bay campus, the Chase Center Arena, home of the Golden State Warriors. This building included about 950,000 square feet of enclosed space, as well as a 2-level parking garage. And it holds about 213 events per year, ranging from NBA basketball games to concerts, family events, and a myriad of other venues. And at maximum capacity, it can seat about 18,000 to 18,500 occupants. The systems for this building included IDEC units serving the bowl of the center. This is the seating area, the playing area, and the largest volume within the building. This provided ventilation not only to the seating area, but also to the occupant suites and also indirectly conditioned the concourse surrounding the bowl area. Other spaces throughout the building were served with water source heat pumps, chilled water, air handling units, with hot water heating as well. And the heating and cooling was primarily provided to these systems with heat recovery chiller connected to a building-wide heat rejection loop. The heat rejection loop also served as a heat source and a heat sink for those water source heat pumps, as well as water-cooled food service equipment. Cooling towers were used along with condensing hot water boilers to supplement and keep the temperatures within the loop within acceptable temperature ranges. And then LED lighting and controls were used throughout the building. And similar to other buildings, the office buildings, the 2009 LEED for new construction gold certification was the energy and sustainability goal for the project, as well as achieving utility incentives through the Savings by Design program. So as I mentioned, one of the keys to energy efficiency on this project, and really the heart of the HVAC system, was the hydronic systems and the heat rejection loop. So I'll walk you through this this diagram to kind of show you how it worked. Starting with the cooling coils and the air handling systems, this cooling chilled water was provided by the heat recovery chillers. Heat recovery chillers rejected this cooling load to the heat rejection loop. The heat rejection loop, as I mentioned, served as a heat source and a heat sink for the water source heat pumps, the water-cooled VRF systems, ice makers and walk-in coolers, as well as crack units. And so in order to, and then also to provide heating for the building, there was a heat rejection to hot water heat exchanger that was used to provide hot water to air handlers and unit heaters, fin tube radiant heaters, and VAV boxes. Boilers were used to supplement the heat rejection loop, and the cooling towers were also used through a heat exchanger to handle any excess heat rejection that other building systems couldn't use effectively. So similar to the office buildings, we conducted a load reduction analysis for this building. And glazing, again, was a source of concern and interest for the project team. And so we were using a pretty efficient insulated glazing unit for the project initially as the basis of design. Used it's a 1-inch IGU with a Viracon 65 low E coating on surface number 2. But both we and the architect were interested to know what would be the effect of using what they called less clear glass, or glass that had a lower solar heat gain coefficient, lower visible light transmittance. And so we used this in the energy model to assess what the effect was. And we also had help from the contractors to provide the first cost estimates of the HVAC systems. And first we found that with the VRE 59 coating, it had even though all three coatings had the same U value, they had different effects on solar heat gain and visible light. So with the VRE 59, we saw not only was there a decrease in energy costs, but also there was a reduction in the HVAC costs. And so much of this garnered us, it would have garnered us 3 additional lead points from what we were originally projecting. Looking at the VRE 54 coating, we saw that it had a much greater reduction in cooling load, but actually increased our heating load. And even though it had a greater first cost savings than the VRE 59, it resulted in overall energy cost penalty for the building. And so this is due in part due to the increased heating cost, but also due to some increased lighting energy. The idea there was that as you reduce the visible light transmittance on your glass, you're reducing the effectiveness of any automatic daylight harvesting controls that we had in the building. So this is the case. And so by iterating between different glazing types, we recommended to the architects the use of the VRE 59 coating. The architect agreed, and that became the basis of design going forward. Later in design, we looked at the kind of refining the design of the HVAC systems and addressing some recommendations that came up as a part of the value engineering or value analysis from the contractor. One of these items was they suggested removing runaround coils from some of the air handling units. And so we investigated that, and going back to our climate analysis and reviewing the energy codes from Title 24 and ASHRAE 90.1, we already knew that enthalpy wheels really weren't recommended for this climate zone due to the low ambient dew point temperatures. So there's not a lot of outside air moisture that we would need to dehumidify with the enthalpy wheel. And so even with the runaround coils, we thought, well, even these may not be ultimately effective, very effective. So what we did is using the energy model, we removed the runaround coils, and we tried to maximize the use of air side economizers. And the model showed that, with removal of runaround coils and the maximization of the economizers, this resulted in a reduction in fan power, as well as due to the fact that now we didn't have this additional pressure drop that the runaround coils had provided, and ultimately provided savings for the design so the team accepted this particular value analysis recommendation. And again, it's somewhat nice when our energy model kind of validates the results of the climate analysis. A climate analysis by itself is not an energy model, but as I mentioned before, is useful in helping to identify potential energy conservation measures that we can later test in the model. And this is a good example of that. So finally, when the project design was done, the major energy conservation measures that helped us to achieve achieve our goals were a high performance building envelope, the water source heat pumps and water cooled VRF systems that were tied to this heat recovery chiller, not to mention the IDEC units I mentioned before, condensing hot water boilers, variable speed fans with static pressure reset, and then LED lighting with daylight harvesting controls. So overall, this provided a 52% energy savings to the ASHRAE 90.1 2007 baseline, which LEED used to award energy points. And we earned 14 of those due to the fact that we saved 37% energy cost savings. The difference between the energy savings and energy cost savings being due to the kind of different amounts of savings between the natural gas and electricity for the building. And to round things out, the arena was also pursuing utility incentives through California's Savings by Design program. This Savings by Design is California's non-residential new construction energy efficiency program. It is funded by utility customers through gas and electric surcharges. And for this particular project, we were working with Pacific Gas and Electric. And essentially the way it works is that the owner is incentivized when the energy performance of the design is shown to exceed 10% compliance margin over the Title 24 baseline model. That's kind of the minimum bar you have to jump over before you even qualify for the program. And after that, there is a sliding scale for savings, at least for electrical consumption savings, that goes from 10 cents per kilowatt hour up to 40 cents per kilowatt hour, as you say, between 10% and 40% energy consumption. Additionally, there are savings for electrical demand and as well as for reductions in natural gas consumption. In addition to the savings awarded to the owner, the design team also has the opportunity to earn utility incentives equivalent to a third of what the owner has earned. And so the method we used to get these, to go through the SBD process was to start with our LEED energy model that was produced in the IES virtual environment, and to modify it based off of specific guidance for the Savings by Design program. The demand savings were calculated based off of the California Climate Zone 3, where San Francisco was located, based off of the average peak demand savings during a specific time period. In this case, it was July 8th, 9th, and 10th, between the hours of 2 and 5 p.m. Additionally, in order to comply with the Savings by Design program, we had to show that we use the energy model to aid in more energy effective, energy efficient design. And so in addition to those other measures that I mentioned before, we also evaluated the savings and payback of additional wall insulation, LED sports lighting, and LED general interior lighting. And so as a conclusion of this analysis, we were able to show that the project was able to achieve much more savings and really earn much more incentive than the Savings by Design program allowed. And so we met the maximum cap for the owner of $150,000. The design team was awarded a $50,000 incentive, and they kind of rounded out our energy performance analysis for the building. So that brings us to the end of our formal presentation. On behalf of Eric, I want to thank you for tuning in. I hope you've come to understand kind of the key features of the sustainability approach and energy efficiency, high performance design approach to the facility. And you see how we use energy modeling early and often throughout the design process, from optimizing and integrating the different performance aspects of the glazing systems in the gatehouse to load reduction analysis in the office buildings, refining the design of the HVAC systems in the arena, as well as aiding in the value analysis, value engineering process. And if you want to learn more about the same kind of approach that we used, I would encourage you to look into ASHRAE Standard 209, Energy Simulation Aided Design for Buildings, which covers many of the energy modeling approaches and cycles that we use for this project. So thank you very much.
Thank you so much, Clark and Eric. We will be entering the Q&A session right now. So if anyone has a question at all, please use the Q&A function at the lower part of your player and submit them, and we will go over them. So I have a first question lined up for both of you. When you find variance in the results of an energy model from actual performance, what tends to be the reason? Is it a flawed model, exceptional weather conditions, or other?
I'd probably say all of the above. Energy models, especially when done for code compliance, would assist in a more highly effective building. Really, it's like looking at the miles per gallon sticker on a car in a car lot. You have specific test conditions, weather files, operating conditions that you're assuming, just so you can make reasonable comparisons between different options. But when we do see differences in actual energy performance of a building versus what was estimated during the design process, now you're right. There could be differences in the typical weather file that was used during design versus the actual weather. There could be differences in the operation of the building or the operating schedule from what was used during design or during operations. There could be variations in the utility rate structures that were used, as well as perhaps there are systems that are operating perhaps differently than was intended by the engineers of record and the design team. And so this is always a good opportunity. For that reason, it's a good opportunity to have other services and to help our clients and owners with other services like monitoring-based commissioning, measurement verification, try to identify what those differences are and how to mitigate those so that the design can meet or exceed the design phase energy performance.
Thanks, Clark. As a reminder, if you have a question, please feel free to submit them to the Q&A button. I have another one lined up for you. It seems the role of energy modeling is increasing in many venues. Is that a trend you see continuing, and what do you expect we will see in the future?
So yes, I think we have and will continue to see a lot of change throughout with more energy modeling being used. For one reason being the fact that energy codes are getting much more stringent. And when that happens, those prescriptive requirements get really are kind of cranking the screws down on what's being required and what's being asked for from architects and engineers. In some cases, design teams may feel that maybe stifling their design creativity. And so using energy modeling for no other reason is I foresee being used more often just to comply with codes. In addition to beyond code rating systems like LEED or things like segments by design. And so I think we'll continue to see specialized software for code compliance like CVAC-COM being developed. We see the energy codes like ASHRAE 9.1 standardizing their Appendix G performance rating method to have somewhat of a stable baseline that makes it easier and faster for design professionals and energy modelers to use energy modeling for not only for code compliance, but also for beyond code rating systems.
Clark, the only other thing I would jump in and say is, you know, I think we're feeling like hopefully the AEC industry, you know, and many of us on the phone as energy and sustainability consultants are embracing energy modeling as an opportunity, you know, not another step or constraint, but, you know, energy modeling in our experience has a very high ROI. I think, Clark, with our own firm's metrics, we usually see a 3 to 6 month payback on the fees for energy modeling. And I think some other third-party, you know, studies have shown, you know, the payback for modeling is typically a matter of a handful of months. And so it's, you know, hopefully we can all brace it as an opportunity to, you know, further energy efficiency and help reduce cost overall on our projects.
Okay, we have a couple more questions lined up, about 3 more. Let me get through them. Can we calculate the total energy consumption for the whole sector by taking an average value of specific energy consumption from 2 or 3 plants and then multiplying it with a total production capacity?
This seems like I'm not sure if this is a generalized question or something specific to this particular project. I may need a little more context to fully answer that question.
They say it's specific. However, I don't have details.
2 or 3 plants. Okay. I will say that for this particular project, the entire central plant was modeled inherently in the energy model, so there wasn't a need to break it out separately and try to piece it back together with weighted averages. Depending on who you're trying to present your results to, you know, whether it's a lead reviewer or a code official, you'll have to work out with them whether that sort of approach of breaking out piecemeal and doing a weighted average is acceptable to them.
Okay. This next question is maybe more of a comment or discussion starter. Currently, I'm working on energy modeling of the foundry sector in Pakistan, and I'm facing difficulty in calculating the total energy consumption of the sector while having specific energy consumption data of only a few organizations from the said sector. The problem is this foundry sector is further divided into different subsectors and different kinds of technologies are being used in each subsector. And there is a large variation in energy use from organization to organization.
So yeah, I assume this is maybe from the previous questioner or commenter. You know, this may be a good opportunity. This may not be, I don't think this is particular to this presentation or to the Chase Center arena and the project. And I'm not sure I can directly address it right now, but I'd be glad to follow up later and we can perhaps collaborate on how to best address your questions. So sorry for not being able to speak off the top of my head right now.
Yeah, Sam, we're glad, you know, I don't know if our contact info is available, but otherwise folks can email the ACG and, you know, Clark or I'd be glad to follow up one-on-one with that colleague, so.
Yes, feel free to email me at sam@commissioning.org and I can forward any questions over to the presenters. There is just one last question in the chat. Someone is asking, what is IDEC?
Right, so IDEC, it's short for Indirect Direct Evaporative Cooling, and that was the technology that was used on the office buildings as well as the arena.
Okay, thanks, Clark. Well, I think that's all the questions that we have for today, and I want to thank you both so much for coming here and presenting with us. I want to thank everyone again who joined us, including our members across all 3 affiliated organizations. We're so glad to have this opportunity to virtually connect with everyone. Everyone participating should keep an eye out for an email with information regarding your learning units from the ACG CX Energy app. While you're in this app, I also ask that everyone please take a moment to evaluate this presentation. We'll be continuing our webinar series next month, September 10th, with how monitoring-based commissioning changes the commissioning business model. Please also make sure to mark your calendars for CX Energy 2021, taking place April 20th to 23rd in Dallas, Fort Worth, Texas. Have a wonderful day, everyone, and stay healthy.
Thank you. Be well, everyone.